Okay, welcome back. This is 5.7, and this is one of my favorite sections, really. Um, so it's on recurrence, solving recurrence relations by iteration. Okay, so in the next section, we'll give you more of a mechanical way of, getting the recurrence, getting the, what do they call that? The explicit solution for a recurrence relation. Um, which is your general formula, right? We don't want the recurrence relation. We don't want like a sub n equals a sub n plus 1 minus a sub n minus 3 or something. We don't want that. We want the a sub n equals 3n plus 1. That's what we're after. So there'll be two methods. This method is cool. It's like you're looking for a pattern, right? What you're going to do is they'll give you a relation, and then you're just going to populate it with a bunch of values from the sequence, a bunch of terms from the sequence, and then you look for a pattern, right? And then you just guess the pattern, and then you prove the pattern works by induction. Okay. Okay. So, anyways, this is called the method of iteration. And we get another method in the next section, which is kind of more of a differential equations type. If you've taken that class, if not, it's okay. It's not a hard method. Okay. So, anyways, let's go back to the Tower of Hanoi. In the last section, we were able to speculate a formula for that: 2m sub k minus 1 plus 1 for k greater than or equal to 2, and then we have this initial value of 1. Okay, so this is a recurrence relation. What we're after is an explicit formula for this. So we can just basically, if we want to know how many moves does it take to solve Hanoi Tower that's 100 donuts tall, how can I figure that out without having to know how many moves it takes to solve a Hanoi Tower puzzle that has 99? Donuts on it, right? So you need to know the previous value before you can get M100 and etc. Let's take a look, and it's just we're just going to look at the terms of the sequence, right? So M sub 1 starts at 1, and then we use the recurrence relation to get the next terms. M sub 2 is 2 times the previous one plus 1. So it's like 2 plus 1. One mistake that a lot of starting students make, like I see it in calculus, is they'll try to add everything together. And you want to keep things kind of separate so you can identify the patterns. If you add everything together, the patterns will sometimes become obscured. And you don't have the familiarity yet. Well, some of you probably do, but there's some of you in there that don't have the familiarity yet to pick out the patterns and apply formulas that we have kind of embedded in the book, right? So yeah, don't rewrite this as don't rewrite M2 as 2 plus 1 equals 3. Just keep it separate. M sub 3 then is 2 times M sub 2 plus 1, and then you could simplify that a little bit. This will be 2 squared plus 2 plus 1, and then M sub 4 is 2 times M sub 3, 2 squared plus 2 plus 1 plus 1, and then that's equal to 2 cubed plus 2 squared plus 2 plus 1. And then hopefully it's becoming kind of obvious that there's a pattern there, right? And it's a familiar pattern based off this formula that they gave to you, right? So 1 plus r squared plus dot 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 plus r to the n is equal to the sum from I equals 0 to n of r to the I, and then we have a closed formula for that, right? It would have been r to the n plus 1 minus 1 all over r minus 1. Okay, so there's all kinds of these formulas. Hopefully you've sort of been cataloging them as we go through the book. So some other ones, obviously, the sum of 1 from I equals 1 to n is equal to n. The next step up, the sum of I equals 1 to n of just plain old I is equal to n times n plus 1 plus all over 2. And we had 1 for I squared last time. You know, those things, you use those. So anyways, we're after this m sub n formula, and from the looks of it, you know, judging in the back, so let's kind of see where the pattern is, right? So if it's m sub 3, then the first exponent on the 2 is 2, right? If it's m sub 2, the first exponent on the 2 is 1, right here. If it's m sub 4, the first exponent on the 2 is 3. Right? So if it's m sub n, the first exponent on the 2 must be 1 less than n. And then the exponents go down by 1 every time, right? So this is 1, and then this one is exponent 0. Down here, 3 times 2, 3, then 2, then 1, then 0, right? So our terms here will be 2 to the n minus 1 plus 2 to the n minus 2 plus 2 to the n minus 3 plus dot 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 plus, and it always ends in like 2 squared plus 2 to the 1 plus 1, right? Okay, so this is a formula for m sub n, but we don't want that yada 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 dot 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 baloney in the middle. So we use that formula that I had just written right up here to rewrite this in a closed form, right? So our R value in this case, the common ratio, is 2. So this should equal then 2 to the, let me get out of that color. Oh, great. Yeah, so this should be what? Using the formula with the yellow arrow pointing to it there, it's normally r to the n minus 1 all over r minus 1. Our last term, so for this formula to work, this n is the n you're seeing right here. Okay, in our case, the n is this n minus 1, so it's a little weird, right? You can't write 2 to the n plus 1 minus 1 over 2 minus 1. You have to write 2 to the thing in blue, I just circled, n minus 1, and then you could go plus 1, so this part of it is changed, right? So it's 2 to the n minus 1 plus 1 minus 1 all over 2 minus 1. And then you could clean it up. You get 2 to the minus 1 plus 1 is just 2 to the n minus 1. 2 minus 1 is 1. And then that's just 2 to the n minus 1. And that's our guess at an explicit formula. And there's no yada 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 in here. There's none of this m sub n minus 1 in here. It's just a nice closed form. That's our guess for the explicit formula solution. Okay, so our kind of quote-unquote solution to the recurrence relation. Okay, great. Let's do one more. Let's try number 12. They can get really complicated. I have one in my notes that's really complicated. If you want to see it, you can ask later, but I'm not going to do it. It's just too complicated. So s sub k is equal to s sub k minus 1 plus 2k for integers k greater than or equal to 1. The initial value is 3. And okay, so let's go at it. Let's just start iterating, right? So s sub 1 is the previous guy, 3, plus 2 times the particular k value, which is, you know, the 1 here. So it's 2 times 1. Okay, let's just leave it at that. Okay, I'm not even going to mess with the 2 times 1 part. So s sub 2 is going to be the previous s sub 1, which is 3 plus 2 times 1. And then plus 2 times the k value, which now is 2. S sub 3 is going to be the previous s sub 2, so s3 plus 2 times 1, plus 2 times 2, and then plus 2 times the current k value, which is 3. And then you kind of see, oh, there's kind of this pattern, right? It's just 3 times, whoops, I didn't mean to do that. 3 plus 2 times 1 plus 2 plus 3. Okay, this guy before it was 3 plus 2 times 1 plus 2. And the guy before it, just 3 times 2. Let's do one more, just in case you don't see it. You can almost guess what it is, right? It's going to be 3 plus 2 times 1 plus 2 plus 3 plus 4. So you go and add all the integer values from 1 to the k value. So I'm pretty sure that's our formula, so I'm going to go ahead and write S sub n is going to be, and you just keep on iterating. If you don't see the formula, you got to keep iterating until you do. So anyways, it's going to be 3 plus 2 times 1 plus 2 plus 3 plus, and you go all the way up to the particular k value, which in this case is n, plus n. And then we got to get rid of that yada 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 business, this dot 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 stuff. That's a no-go. No-go. Okay. Right, so we had a formula for that kind of junk from above. Let's go and look for it. It's this guy right here. Okay, that thing, that sum from 1 to n of I is 1 plus 2 plus 3 all the way up to plus n. So I could replace that with n times n plus 1. So I'll have n times n plus 1 all over 2. Okay, and then I can simplify. So this would be 3 plus 2's cancel, you get n times n plus 1, which equals 3 plus n squared plus n, which equals n squared plus n plus 3. Okay. And that's our, quote unquote solution or explicit formula or closed form, whatever you want to call it. I don't think anybody's really landed on a moniker for that guy yet. Okay, so there it is. Now it's a guess, right? I mean, ultimately it's a guess because there was yada 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 business going on here. So how do we make sure it's a solution? We're going to be doing that with using math induction. Okay, of course. So checking solutions with induction. So we'll just say checking by induction or something. Okay, so let's go ahead and just play around with the formula we just found. The way it's going to work is you'll have a definition for the sequence given recursively. That's going to be given information that you could use in your proof. So let S sub 0, S sub 1, S sub 2, and we've kind of already done these proofs in a previous section, but let's just go through it again. Let that be a sequence satisfying some recursive relation. Okay, so it's S sub k equals S sub k minus 1 plus 2k for k greater than or equal to 1, where you have an initial value of 3. Right, so that's the given information. And then we have our solution somewhere from iteration. We found it, and then we want to show it's true, right? So we want to show that S sub n equals n squared plus n plus 3 is a solution. For n greater than or equal to 0. Okay, so we're going to do this by induction. So proof by induction. The first, your basis step, then we look at P of 0. P of 0 is S sub 0, which equals 0 squared plus 0 plus 3. So I'm just plugging 0 into the predicate that I'm trying to prove, and the predicate I'm trying to prove is right here. Okay. I want to prove it's true for n greater than or equal to 0. Okay. Okay, so that's going to be the left-hand side S sub 0 from the given information is 3. The right-hand side from arithmetic, 0 squared plus 0 plus 3 is 3. Okay, so hence the two sides are the same. And it holds. The P of 0 holds. So the basis step is fulfilled. Now we go on to our inductive step. Okay, so part 2. We want a supposed or supposition. K is a payback integer such that K is bigger than this value from the basis step, such that K is greater than or equal to 0. And P of K is true, so P of K would be the S sub K equals K squared plus K plus 3. Of course, we want to show S sub K plus 1 follows. S sub K plus 1 from our explicit formula is K plus 1 squared plus K plus 1 plus 3. We want to simplify that a bit. In other words, let's just simplify it in this statement though. So we get K squared plus 2K, doing some foiling, plus 1 plus K plus 1 plus 3, and then that will equal K squared plus 3K plus 5. Okay, so that's what we want to show, and we'll start on the left hand side with S sub K plus 1. Note S sub K plus 1, and here I go and use the given definition of S sub K from the recursive definition. So S sub K is equal to S sub K minus 1 plus 2K. All right, so let me just note that in the etherness here so I can reference it. S sub K is equal to S sub K minus 1 plus, I think it was 2 times K, or maybe there was a 3 in there somewhere. No, that's it. Okay, so in order to write S sub K plus 1, you just replace these K values with K plus 1, and you'll end up with S sub K. Whoops, let me put that in white. So I end up with S sub K plus 1 minus 1 plus 2 times K plus 1. So I also have to put it in there. So I have to replace that K with a K plus 1. And then that will be S sub K plus 2K plus 2. And then you could use your inductive step to rewrite S sub K, which is K squared plus K plus 3. Okay, sorry, I hit the pen. K squared plus, by the time K squared plus K plus 3, and then plus the 2K plus 2, and that will equal K squared plus 3K plus 5, which if you look above, that's what we wanted to show, right? Okay, which is what we wanted to show. Hence, the explicit formula works, and we can all sleep well at night and all that jazz. Okay. So this stuff is awesome. As far as math goes, this is one of my favorite subjects. Finding these closed formulas for recurrence relations. Oh my gosh, just really, in my opinion, where it's at. Okay, so we'll let you go there, and we'll see you next time.